So we're going to be talking about some acid-base theories right now. So first, the Arrhenius theory, and that is one that you have already had me discuss in class. This is what I like to call the HOH theory. Let me get back up here, acid-base theories. There we go. So Arrhenius was a Swedish chemist, Nobel Prize winner. Check the years out there. He's one of the first chemists to explain chemical theory of behavior of acids and bases. So I like his Dr. Cotton's last little factoid here. Dr. Hubert Aleya, I'm not sure how to say this, was the last graduate student of Arrhenius. And I'm sure he put this slide in here because of this happy chemist slide. That is one of the happiest chemists I've ever seen. And he was the last graduate student of Arrhenius. So what exactly is the official definition of the Arrhenius acid and base? Acids, as you know, produce hydrogen ions. I'm looking for my edit thing here. I'm supposed to be able to edit on here. It's not letting me edit. Maybe I just won't be able to edit. So the Arrhenius definition of acids and bases: acids produce hydrogen ions. And as you know, all the acids that we've discovered or that we've studied up to now start with hydrogen. For instance, hydrochloric acid, nitric acid, HNO3, sulfuric acid, a diprotic acid, H2SO4. Bases produce the hydroxide ion when dissolved in water. The Arrhenius definition of acids and bases is limited to only solutions in water. Only one kind of base is considered or described by the Arrhenius definition of acids and bases, and those are acids that contain the hydroxide ion. Ammonia, NH3, could not be produced from Arrhenius base. If you look at ammonia, there's no OH1- produced. I want to make a note here. If I was doing this on PowerPoint, if I could edit this on PowerPoint, which I can't for a wide variety of reasons, these superscripts and subscripts would be showing up. So I apologize for those not showing up. There he is. This is another thing we've talked about already, polyprotic acids. A polyprotic acid is a compound that has more than one ionizable hydrogen. Look with me at HNO3. Please notice the HNO3. That is a monoprotic acid. It has one ionizable hydrogen. Sulfuric acid, H2SO4, is a diprotic acid. It has two ionizable hydrogens. And if you start trying to connect this with what you know about stoichiometry, you'll see that there are stoichiometric implications for mono, di, and triprotic acids. Probably the most common triprotic acid that we'll be using is phosphoric acid. Now please note that having more than one ionizable hydrogen does not have anything to do with strengths of acids. H3PO4, phosphoric acid, is in fact not a strong acid. Not all compounds that have hydrogen are acids. Under Arrhenius definition, water cannot be an acid. Another one that you might be familiar with is hydrogen peroxide, H2O2. Not all the hydrogens in an atom are released as ions. Those that have very polar bonds are ionizable. For instance, HCl, hydrogen has a relatively low electronegativity, and chlorine has a high electronegativity. That would make the HCl bond very polar. So the hydrogen is joined to a very electronegative element. HCl. And I just talked about that one. And remember, if I had a pen right now that I could write with, I would be putting a delta minus by the chlorine, and I'd be putting a delta plus by the hydrogen. Let's consider methane. Please remember that methane is carbon bonded to 4 hydrogens. It is a nonpolar molecule and it bonds in a regular tetrahedron. So it is a nonpolar tetrahedron. Since it's nonpolar, it is not easily ionized. Ethanoic acid, which is CH3COOH, has 4 hydrogens total. The only ionizable hydrogen is the hydrogen at the end, the one that you see on the very left of the the very right of the ethanoic acid. The CH3, the methyl group, is bonded to the C double bond OH, which you'll see at another point. So there is a table. This will not be the right page number or probably table number, but it is in section 19.1 for bases show metallic hydroxides. Now here are those organic acids, and I mentioned this Monday. And organic acids are acids that contain carbon. Now this does not include carbonic acid. Organic acids contain something called the carboxyl group. And in that white box, you'll see the carboxyl group. There is a carbon double bonded to an oxygen, and that same carbon has a single bond to an oxygen and a bond to a hydrogen. So that hydrogen that's being pointed at there is an ionizable hydrogen. Please note that hydrogen is bonded to the highly electronegative oxygen. The carboxyl group, that C double bond OH, is a poor proton donor. So all organic acids are considered weak acids. That means that they only dissociate to a small extent. Our second theory of acids is Bronstead-Lowry. It is a broader definition of the Arrhenius acid and base theory. In Arrhenius, again, we have a hydrogen ion and a hydroxide ion. In the Bronstead-Lowry theory, we call an acid anything that is a hydrogen ion donor, so a H plus or a proton, and a base, all it has to be is a hydrogen ion acceptor. Under Bronstead-Lowry, acids and bases always come in pairs. Hydrochloric acid, HCl, is an acid when it dissolves in water. Look at this chemical equation on the bottom. We have hydrochloric acid dissolving in water. Please notice that the hydrochloric acid, HCl, loses a proton and becomes Cl minus. So on the product side, we see a chloride ion. So HCl turns into, if you will, the chloride ion. More interesting, or of great interest to me, let's look at the water. You'll see on the reactant side, H2OL. This turns into, it accepts the proton and turns into H3O plus, which is the hydronium ion. In this case, water, H2O, is accepting a hydrogen ion, which means that water is behaving as a base. In this case, water is a base. So on the reactant side, we have HCl, which is an acid, and H2OL, which is a base. If you need to stop here a second and look at this, feel free. Oh, what did I touch? Bronstead-Lowry. Let's look at ammonia, NH3. So ammonia can be classified as a base by using the Bronstead-Lowry. Please look at this chemical equation. On the reactant side, we have ammonia reacting with water. You'll notice that ammonia accepts a hydrogen ion to become ammonium ion. And that should be NH subscript 4 superscript 1 plus. But again, I can't make it open correctly on my computer right now. on my iPad, so that is what it is. And you'll notice that water in this case, H2O, look at the water, is donating a hydrogen ion, and the remaining particle after the hydrogen ion is donated is the hydroxide ion. So ammonia is the hydrogen ion acceptor. Remember, under Bronstead Lowry, a base is a hydrogen ion acceptor. NH3 accepted a hydrogen ion. Water is a hydrogen ion donor. So water is behaving as an acid. On our previous slide, water was behaving as a base. On this slide, reacting with a basic substance, water is acting as an acid. So what happens when we put these two reactants together is the hydroxide ion concentration increases. The ammonia solution becomes basic. We had mentioned earlier that under Bronstead-Lowry, the acid and bases always come in pairs. A conjugate base and a conjugate acid are the particles that remain after a substance donates its hydrogen ions. And we'll look at these in a moment. So let me just give you a moment to look at this slide. Conjugate acid or conjugate base is the substance that remains after the original acid. The acid on the reactant side loses a proton. So just look on the product side for whichever species is one proton short. That's your conjugate base. Also, you have a base on the reactant side. The conjugate acid of that base is the species that's left that has one additional hydrogen ion. So a conjugate acid-base pair is related by the loss or gain of one single hydrogen ion. Indicators, and you're going to do an indicator lab next week, are weak acids or bases that are different colors from their original acid and base. So they're conjugate acid-base pairs that, Bronstead-Lowry acid-base pairs that change color. Acids and base come in pairs. Let's look at this general equation. HA is an acid, reacts with water, and you'll see that it's H3O and minus. Next, there's my acid, HA. My base is H2O. My conjugate acid is H3O plus, and my conjugate base is the A anion. So take a look at that. I wish I could write on here. I would make the HA and A one color. That's my acid and conjugate base. My water and hydronium are my base and conjugate acid. Let's look at the next example, ammonia and water. My ammonia and ammonium are my base and conjugate acid. Water, H2O and OH, water is my acid, and OH, the hydroxide ion, OH1 minus, is my conjugate base. Let's look at the next one. This is sort of a fun one. You'll notice water can act as either an acid or a base. This is a substance called amphiprotic or amphoteric, a substance that can act as both an acid as a base. So that's amphoteric. I often call those amphiprotic. So if you hear me say amphoteric or amphiprotic, I mean the same thing. Lewis acids and bases are our most inclusive theory, and we call Lewis acids and bases electron pair acceptors. Lewis acid is an electron pair acceptor, and the Lewis base is an electron pair donor. It's the most general of all three. Acids don't even need a hydrogen. And I'm going to see, there's a summary table in your text. Again, this will be the wrong page number, and it might be the wrong table, but you should have an acid-base table in there. not even going to guarantee that, but I'm pretty sure you do. There's Sullivan Lewis, and here is, this should be in your text. Please notice in this problem, if you look carefully, there's ammonia, and if you can see, there's an electron pair hanging about on that ammonia ion. The boron trifluoride, which is, if you'll recall, boron is an exception to the octet rule. It forms a trigonal planar boron trifluoride molecule. However, it still would prefer an octet. So you'll notice that boron, from the reactant to the product side, is accepting an electron pair. An electron pair acceptor is classified as a Lewis acid. Ammonia, which you already know is the base, is donating an electron pair to that bond. So ammonia is an electron pair donor, which classifies it as a Lewis base. I think that's it. Okay. That's it.